Then I will share my screen. Okay, so last time we got to about here. Does anybody have any questions about balancing nuclear reactions or
could we review it once more?
balancing nuclear reactions?
Yes.
Okay, well, we could look at anything, really. So let's just see if I got something simple over here. So look at this one right here. So look at the number of protons. So there's 19 over here, and that -1 mathematically is now 18. So it has to equal 18. So if I didn't have this part over here, you could still figure out that that should be an 18. And then you could go to the periodic table. What is element 18? Well, it turns out to be argon. And 40 plus 0 would still have to be 40. So what happens here is that potassium 40 undergoes electron capture, and a proton gets converted into a neutron, and you end up with argon 40.
So this is in effect an atom, an element changing into another element because it's a nuclear reaction.
Exactly.
In which it's absorbing an electron, and therefore potassium turns into argon.
Exactly.
Okay, nice.
So that's the whole scheme of it here. So if you just look at this part right here, right? Could you figure out what was here if you had this and you had that? Well, 92 is equal to 92, so that's got to be a 0. And then that's 236. That's 236. Or if you had this is 236 and that was 235, that would have to be a 1. So what has 0 protons but still has a nucleon? It's got to be a neutron.
Right. So it just changes. In this case, it's an isotope of uranium.
Exactly.
From 45 to 236. Now, what about on the other side of uranium?
We had only this right here. Say you had everything except for this, right? Well, 92 is going to have to be equal to something plus 36 and 0. So that means that would have to be a 56. And the periodic table tells you that element 56 is barium. And then, okay, what number is for the mass number? Well, 236 has to equal 92 plus 3 more of these, right? So that's 95 minus 236 would give you 141.
So this equation here is showing that uranium-236 is turning into barium and I don't know the Kr.
Yeah, krypton.
Krypton. But if you were solving for this and all you had was uranium on the left side, how would you know that it was those elements on the right I mean, how would you know that it would be those elements on the right?
Well, you wouldn't.
Couldn't it be?
There's no way you could know that.
Okay.
You have to be given some information.
I see.
Yeah. So you just need to know how to figure out what information is missing. You don't need to have the whole thing known or anything else like that.
Okay.
Yeah.
That's very clear. Thank you.
Okay, good. Okay, so what about in our lives? Well, in certain parts of the mainland, they do have a problem with radioactive radon gas coming into people's houses. It comes from the decay of radium that's in the rock below where they're living. So radium will spontaneously decompose by giving off alpha radiation, and then it turns into radon gas. So radon gas is a noble gas. It's on the periodic table. You look at it, it's in red, right? So it's a gas. And so it may take 100 years for that radon gas to percolate through the earth and get to underneath your house. It may take, another year to get through the concrete slab if you have one and get into your room. But the problem is, when did it start? Well, 101 years ago. So you have a constant flow of radioactive radon gas coming into your house. So they actually have radon gas detectors that you can buy. I noticed that one time in Costco they were selling them, but in Hawaii we don't have that kind of ground underneath us, so we don't have to worry about it. Especially on the East Coast, though, you have to worry about that stuff. Then food irradiation has been used for at least 50 years. And so here's some strawberries that were irradiated, and here's the same batch that were not. And so that's why this little boy is extremely unhappy, because look at his strawberries. Sorry, I just saw that on the internet. I had to use it for something. So why would we do this? What is the purpose of irradiating food? Because you're going to kill bacteria, fungi, insect larvae by killing their DNA. You're destroying their DNA with ionizing radiation. And so there is no evidence that irradiation causes any dangerous change in the food. Obviously, the food is not radioactive. So there's less radicals produced in irradiation than in toasting bread in an oven or toaster. The nutrients are less affected by radiation because the temperature doesn't go up. But irradiated food is supposed to be labeled with this radula here. Here's an example of how devastating a disease to a crop can be. Hawaii could not export avocados starting in 1992 when they found fruit fly larvae. And fumigation, which is a chemical way to kill the fruit fly, ruined the taste of the avocados. So it took 24 years before a new variety of avocado that wasn't infected by the fruit flies was allowed to be shipped to at least 34 states. So that devastated that whole industry in Hawaii. And they're constantly trying new things. Here's an example to protect, our crops and everything. And so here's another aspect of it, radioactive labeling, or what's called isotopic labeling. And so look at this. You guys either know about glycolysis or you've actually studied in detail, maybe the citric acid cycle. How do we even know that? It's because of radioactive tracers. So anyway, here's one example. Carbon-11 has a half-life of about 20 minutes. It emits positron radiation, which is then detected as gamma radiation. Okay, so you can count, you can measure the radioactivity coming from carbon-11. So what you can do is make a molecule like carbon dioxide with carbon-11. So you take carbon-11, turn it into carbon dioxide, and give it to a plant. Now that plant's going to absorb the carbon dioxide and turn it into glucose. That glucose is now going to be radioactive labeled. Okay? So I can give a rat or something like that radioactive glucose, And then I watch what happens to that glucose molecule. In this case, it gets converted into pyruvate, which is the end product of glycolysis. So what happens to the carbon in glucose? Well, it turns into a carbon and pyruvate. And if I were to stop it at different parts over here, I would be able to map out all of glycolysis and where the carbon goes from one point to another. Then I have radioactive pyruvate. I can let that go into the citric acid cycle, and out comes at the end carbon 11 in the form of carbon dioxide. So how do we know that the carbon from glucose ends up as the carbon in carbon dioxide that we exhale? It's all because of these radioactive tracer methods. So we could stop it here and here and here and here and look at what we got, and we will see all the intermediates of the citric acid cycle, all with that radioactive carbon atom on it. So these were experiments that were done quite a while ago. It was very messy. I'm sure people got exposed to radioactivity and their lives were shortened because of it, but why'd they do it? Well, to advance science. Once you contribute something to science, you don't even know how important it might be 50 years later. But any contribution is going to be valuable some way or another. So here's some other examples: diagnosis and imaging. So X-rays and CT scans use radiation. So an X-ray is the standard in imaging, especially for extremities. The radiation is equivalent to about 3 hours of background radiation. So it's really not that much. So what I mean by background radiation is like what you're getting from just the environment sitting there in your house. A CAT scan or CT scans means computer-assisted tomography. Tomography is simply the method of converting data into images with a computer. So a CAT scan gives you much more data, but it uses more radiation. And then we have ultrasound and MRI do not use radiation. So ultrasound gives really good detail. It's used in pregnancies, liquid-filled organs such as the heart, things like that. It cannot penetrate bone. And also an MRI gives excellent detail. So I tried to explain how an MRI works. And it's quite complicated. I did the best job I could. But here's the idea. Hydrogen atoms have an odd number of protons. Because of that, they actually are paramagnetic. So if I take a bunch of hydrogen-containing compounds, such as your body, for example, and I put them in a very large magnetic field, I can get those hydrogen atoms to align in that magnetic field. Okay? So now that I have that done, I can take another source of energy, a radio frequency, and I can vary that frequency. And what I'll find that at a certain energy, some of those protons will start flipping back and forth from south to north, from north to south. When it does that, it absorbs energy and gives a signal. If I change the radio frequency a little bit, those will stop vibrating and other ones will start vibrating. So what we do is you put it in a very powerful magnet, whatever you're going to look at, and then you change the radio frequency coil, and you're measuring when energy is absorbed by the substance and when it's not. Okay? So I think, okay, I'll just go through all this. And then we have imaging with radioactive isotopes. So the thyroid gland uses iodine-131. And then the PET scan is basically taking isotope detection data and turning it into images using what? Tomography. Okay. And so I think I'm going to go now to the images. New share. Okay, so that one we saw the last time. So here's a PET scan. So what's happening over here is that you have detectors right here. And so you're giving this patient something that is going to give off a positron. And what do we know about positrons? They immediately collide into an electron, and there's an annihilation. And gamma rays go off 180 degrees from each other. And so what you're really detecting with this detector right here is gamma radiation. So I'm originating from this point right here in the person. I'm getting a detection here and a detection here. So that is the data that's being collected. Where are gamma rays colliding with this detector? So that's the raw data. That now goes into a computer, and then the computer takes it and using the process of tomography, converts that data of light reception into the image that you see. So whoever created this program had to be able to know exactly, well, what am I supposed to be seeing? What should it look like? And how they know that is from looking at people's brains and stuff in this particular case, right? So they have to figure out how to take this signal over here, which is gamma radiation, process it with computer programs and turn it into an image. So here's some examples. Here's a person who has a tumor that's not supposed to be there. Okay. And then here's certain activities of the brain that you can look at. So under this circumstances of this person's brain activity, so here's some high activity in the red, lower activity in the different colors, no activity, right? So actually with this kind of technique, you can find differences between a normal person and a violent criminal. You can see it in CT scans of their brains. Here's an image of a thyroid gland. So this is simply using iodine-131. So if you look at iodine-31, I think it gives off beta radiation. Let me just check by looking at the periodic table. I think I wrote it in there somewhere. Yeah, it has a half-life of 8 days and it gives off beta radiation. So what is the detector really detecting? Electrons. So here's a person's thyroid gland because iodine goes preferentially to the thyroid gland. The reason it does that is that the thyroid gland produces a hormone called thyroxine. So thyroxine as a molecule has several atoms of iodine on it. So if you give this person radioactive iodine, it will go to its thyroid gland, and when it gives off the beta radiation, it can be detected. So here's what a normal thyroid reading should look at. Here's a Graves' disease, where what's it doing is making too much thyroxine. Here's some other bad situations, but it's supposed to look like this. And here we're also looking at the thyroid gland, but we're looking at it with ultrasound. What ultrasound does is it sends sound waves through the tissues, and the tissues absorb the energy from the sound waves depending upon their density and a whole bunch of other factors. So here's an image created from this machine. So these do give you different information. This is different information than this, even though it's the thyroid gland. So any questions so far? Let's see what happens here. Okay, here we go. So then we also use it in radiation therapy, radioactivity, mostly in cobalt-60. So here's cobalt being bombarded by X-rays, and then we get the metastable nucleus. Okay, so nothing has changed here. No nuclear reaction has really happened. We just have an unstable nucleus. And then when it becomes stable, it gives off gamma rays. Okay. So what will we use this for? It's used to kill cells. So what you do is you aim it at the tumor to kill the tumor cells. You're killing those tumor cells by destroying their DNA. So to spare the normal tissues from being damaged, having their DNA damaged, they've learned to really, really control how the radiation enters the body. And say, for example, you had the tumor in your chest. Say you had a tumor in your lungs. How are you going to aim that gamma radiation at the tumor and do the minimum damage to the rest of the tissue? We have to realize that you don't want to damage the person's heart. So you're going to have to come from the back and from the sides and from the front. You're going to do everything you can to not cause damage to the person's heart. The other thing that you want to do is you maximize damage to the tumor and minimize damage to all the other tissues. So you don't just aim it and just hold the trigger down and just keep blasting it, because you'll destroy everything that's between that tumor and the source of the radiation. So what you have to do is come from all different angles to minimize damage to the tissues and maximize damage to the tumor. Anyway, there's a whole bunch of different problems that come with this. One of the problems is it's called the Warburg effect. So what they found many, many years ago was that tumor cells have a different metabolism. They rely a lot upon glycolysis, not as much on aerobic metabolism. And so the problem with tumors is that they don't have a lot of oxygen in them. And how do we make most of our free radicals? They contain oxygen, like the hydroxyl radical. So what's really going on here is that irradiation is more likely to kill a normal cell than a tumor cell. So this is a problem that has to be overcome. So what they do is they have drugs that increase the oxygen in those tissues. They just use a lot of different things. They will try to put radio-sensitizing drugs, some cytotoxins in there, stuff like that, to also enhance the effect on tumor cells and reduce the effect on normal cells. So to be a radiologist, there's basically two kinds, right? Radiologists oftentimes simply read images. They can do that from home even. But if you look at people who work in radiation therapy, oncologists, that's a totally different story. These guys have to really know what they're doing. So questions so far? So nuclear fuel and bombs, I don't want to go into it a lot. I did in chapter 7, which we're not covering because I wrote a lot of stuff about nuclear fuel. So listen to this. The International Thermonuclear Experimental Reactor. What the heck is that? So what it is, it's a fusion project. And what it tries to do is take hydrogen and fuse it into helium using extreme pressure and heat to overpower electromagnetic repulsive forces to, or what we're dealing with is the nuclear strong force. So right now, there is no fusion reactor that can produce a net amount of energy. In other words, we can make fusion happen, but it costs more energy to get that energy than the energy we get out of it. So the joke is fusion is this 20 or 30 years away and always will be. I probably should take some stuff out of chapter 7 and put it right here. So for one, this is located next to Lake Geneva, and they have figured or calculated that there's enough hydrogen 2 in Lake Geneva to produce electrical energy for most of Europe for the next 1,000 years. And Greenpeace is against this project. The world is complicated.
Why are they against the project?
Oh, look at the word. It's thermonuclear. It's dangerous. It's not natural. Yeah. Now, if we could get the whale union to come out in favor of it, then Greenpeace might follow. So fission is what's used in nuclear power plants. And radium is the starting material because it's found on Earth. You can mine it. So most of it is uranium-238. This is what we want, uranium-235. So you have to separate out the other ones from it. And so one way to do that is you take the uranium after you've purified it, and you basically form a reaction where you turn it into uranium-6 fluoride. And then you vaporize the uranium-6 fluoride. So uranium-6 fluoride contains all the isotopes of uranium, right? You're going to have to put this through the gas diffusion at least 1,750 cycles before you get anywhere near enough enrichment to do anything. So a bomb would need to have at least 20% uranium-235, but an effective bomb needs about 85%, and you're starting out with only 0.7%. And so these are gas centrifuge tubes. So these things are spinning, causing a huge increase in the gravitational field. So what you find is that uranium-238 will centrifuge faster than the other ones. So you do that for a while, and then after you get rid of that, uranium-235 will centrifuge down faster than uranium-234. So here's the process. You want to end up with your uranium-238 in here, uranium-235 in here, and uranium-234 is basically left in here. And what you're doing is these are all semi-permeable membranes. They let larger things not go through the membrane, and maybe a little bit smaller things can go through the membrane. So this first one right here, you want to let 235 and 234 go through it, but the 238 gets stopped over here. And this one over here, you want to keep the 235 in it, and the 235 doesn't stay in it. It goes out through the other one. So now you keep enriching. And you got to do that, 1,800 times or something. So let me go back to that figure again. Cover up my buttons every time I do that. So here's a cartoon of a solid core reactor. And so here's the reactor, right? The nuclear reactor over here. Here's a close-up of it over here. Here's the principle. The fuel rods contain at least 20% uranium-235, okay? And so it gives off neutrons. So say you have something decompose over here, uranium-235 decomposes, gives off neutrons. It's going to go within the rod. It's going to go crossover, go to the next rod, causing these to break down, shoot electrons that way. Not electrons, neutrons. And so if you don't do anything, this thing gets hotter and hotter and hotter and gets out of control. So how you control it is you drop down these control rods that absorb the neutrons and preventing neutrons from this rod to go to the other rod. So if you pull these up, you accelerate the reaction. If you put them down, you decelerate the reaction. So what happened in Chernobyl and possibly in Fukushima, this got so heated that it simply vaporized the control rods, and now you have no control over your reactor. So you get a meltdown. So how does it work? So here is the primary coolant. Many times this is a liquid metal. It's just so hot that it's a liquid. So it's hotter over here, then it cools off in the presence of water, and then it gets come over here and gets heated up again. So the primary coolant loop never is exposed to the environment. In this simplification, they only have one. But in effect, there's going to be a couple of them. You don't want these to be exposed to the environment. But at the end, ultimately, what you're doing is you're taking liquid water, heating it up from the heat that comes from the reactor, and what happens? Oh my God, it turns into steam. And the steam goes through these tubes and presses against the turbine, which is simply a generator. And the word turbine means it has like little fans on it that can actually catch the flow of water vapor and cause it to turn. And a generator is just an electrical motor being forced to operate in reverse. So what you do is you're creating electrical current. So really, what is the only thing that's different about this than in a steam operated generator? is nothing more than what is the source of heat. So I use a small amount of uranium instead of using a whole forest to get the same amount of heat to vaporize the same amount of water that would give you the same amount of turn in the turbine to give you the same amount of electrical power.
So for a nuclear reactor or a nuclear plant, the power is generated by the turn of the turbine, which comes from steam from heated uranium.
Yep. Yep. But again, the amount of heat you get is just fantastic. I mean, look at our nuclear submarines. They can be underwater for basically years. They run out of food before they ever run out of, nuclear fuel. If they were run by gasoline or diesel, they have to come back every month or something. And nuclear submarines are one of the most strategic weapons we have because they can go underwater and stay for so long, nobody knows where they are. So it's a constant battle to know, for the Americans to know, well, where are all the Chinese subs? Where are all the Russian subs? And they have the same problem with us. So that's a big deterrent for war. Yeah, so here's a CAT scan. Copycat, get it? So I don't know how you guys feel about nuclear power. It is not something that's easy to do. It has very high requirement for technology and everything else. So one of the things that these people who are against the 30-meter telescope are saying, oh, it's going to be nuclear powered. And I'm like, where the hell did you hear that? It's just the most ridiculous thing in the world I've ever heard. So there's just no way that a nuclear power plant is going to be allowed to be up on Mauna Kea or anywhere else. Can you imagine if they tried to build a nuclear power plant in downtown Honolulu? Not going to happen. So the technology that we have now to build nuclear power plants is way greater than it was 50 years ago when we started building them. So the fuel rods, the control rods are much better. The fuel rods are much better. And this is what kind of irritates me when you learn about these things. So in the 1970s, they built a thorium-based breeder reactor. It was found to be effective, and then they abandoned the project. So, so in the breeder reactor, the thorium-232, which is not very reactive, captures a neutron. Then you get thorium-233, which then gives off beta radiation, and you end up with uranium. The uranium-233 can be used to do fission. So in other words, you don't have uranium as the starting material. You make it yourself. You breed it yourself. So you don't have to worry about people trying to steal your uranium. And you can generate it whenever you need it. You don't have to store it. Other things that we have are what's called molten salt reactors. And what you're really doing is you're storing energy in molten salt. That's another thing. But it can also be used as what's called a freeze plug. So here's how this works. Here's the nuclear fuel right here. Here's the control rods, right? And so you send salt through here, and that's what you use as your intermediate. Now, what happens if the reactor starts to burn out? If the reactor gets overheated for whatever reason, this freeze plug right here will melt, and it falls into these tanks that are below the ground. So this whole thing will drain out and go underground and be stored. It can never get hotter than the temperature of these freeze plugs. So what is the likelihood of a nuclear disaster? Not much at all. Okay. So here's a few other things. The current stockpile of spent nuclear fuel is about 83,000 tons. So a company is trying to figure out a way to make a molten salt type reactor and use the spent fuel to power this whole cities and maybe the rest of the world. So what they're trying to do is figure out a way to take all of our spent nuclear waste from the old-fashioned nuclear reactors and use it in one of these newer type of more high-tech nuclear power. So when people say, oh, I'm against nuclear power, it's like, okay, what are we going to do with this 83,000 tons of stuff? What are you going to do with it? And if they knew the technology that was available, then I think they wouldn't be against it. Are people going to give up their electricity? I seriously doubt it. If they're not going to give that up, where are they going to get their electricity? From burning forests and putting carbon dioxide in the air? From digging up fossil fuels and putting more carbon dioxide in the air? Or maybe we should take advantage of this 83,000 tons of spent nuclear fuel. In 2017, the US got 20% of its power from fission plants. So we got about 100 reactors, 61 plants in 30 different states. So I thought this was interesting. How did America win the war? World War II. So a lot of interesting things happened in World War II. It was the most amazing group of humans that won that. I looked at my father's generation were in World War II. Most of my friends, their fathers were in World War II. And they had a lot of stories to tell. Most of the time they wouldn't want to talk about it, but Nazi had taken over Norway and made a plant where they were making heavy water that was needed to produce plutonium so they could get nuclear bombs. But these resistance fighters went on a suicide mission. They thought they wouldn't be able to complete the mission. Even if they did, they didn't think they'd survive. But they did. They went in there and they blew it up. There was a movie called The Heroes of Telemark and some other stuff like that. And yeah, you can imagine if the Nazis had the bomb before we did, that would be a problem. So what about chemists during those days? So Heisenberg was German. So he continued to work for the Nazis. So people thought, oh, he's a Nazi. But what he was really doing is that he delayed the nuclear success of Germany, which really allowed the Americans to be the first. And then the son of Madame Curie basically smuggled his notes on fission into England and then joined the French resistance making Molotov cocktails. Of course, he should have spent his time doing science. So here is some energy conversions. I think I gave you this one or somewhat close to it. Oh, here, I gave you that one before. Okay. So a stick of dynamite is about 5 times 10 to the minus 7 kiloton of TNT. A gallon of gasoline is almost 100 times more powerful. But yet, we're not allowed to drive around with dynamite in our cars, are we? But we're allowed to put 20, 25 gallons of gasoline in our cars and then drive at 50, 60 miles per hour with our children in there, as long as we have car seats for them. So the biggest one ever was in 1961, way bigger than the one that was dropped on Hiroshima. So you can imagine what we can do now if we really wanted to. It's very scary. So a couple of years ago, have you guys heard of electromagnetic pulse weapons? So they create this electromagnetic radiation, and this can fry electronics. It doesn't have to be from a nuclear bomb. So about 2 or 3 years ago, I was up at Schofield Barracks. We do we have part of a nonprofit that we help the infantry people up there with a project that they do. It has to do with supporting an orphanage. Anyway, so I'm there with the lieutenant colonel who's in charge of all this stuff, and he's showing me in a mock battle situation how they've situated all their vehicles and stuff like that. And I asked him about EMP. He goes, oh, yeah, it's right over there in that Humvee. So I'm not supposed to know that. You're not supposed to know that, but we all know that these are actually weapons. You fry your enemy's electronics. And so much of the battlefield now is based upon computer stuff, computer guided this and everything else. So why do we keep making more elements? Well, it's kind of like sports for scientists. Some theories suggest relative stability of some elements on the next row. And we need to understand more the complexities of atomic structure. So here's what they did to synthesize technetium in 1937. In 1944, they synthesized americium. 45, they synthesized promethium. Here's how they got technetium. And then what they're trying to do now is create number 119. So if you look at the periodic table, which I can't really see because I'll stop sharing. So here's 118, right? They've synthesized that. What they're trying to do is get 119, which would be a new period on the periodic table. So that's why I'm talking about this. So in 2015, they took titanium and they slammed it into berkelium. So here's a bombardment, right? More than one thing on the reactant side. So here's one scenario. They tried to bombard it, one element into this other element, which is element number 97, and also a man-made element. And then this is what they expected to get. So here's 119. They expected to give off 4 neutrons, and then, yeah, so that's what they expected to get it. They didn't think it was going to last for very long. So far, they have not been able to do it. Different countries are trying different things. But what if they were to make this and it actually became stable? Pretty interesting. So if you guys don't like governments, then you'd enjoy this. So this is a joke. I'll let you read it. It's pretty funny. I thought it was really well done. So what do you do in case of emergency in a nuclear power plant? You run. Yeah. And here's Gilbert doing this thing. And I thought to myself, maybe we need to bring back Chuck Norris jokes. Yeah. Anyway. So that concludes chapter 6. So any questions about anything in chapter 6? Was it a very fun chapter for you?
It's interesting. Radiation and nuclear power. It's a very sophisticated technology, and I never knew actually that it generates the steam, which generates electricity through the turbines. I thought that was very fascinating. I thought it was a lot more. I actually thought it was more complicated.
Yeah.
I mean, it's complicated, but I thought it would be even more complicated.
Yeah. Yeah, it's kind of interesting how it works. So I think it's very important. I mean, hopefully you guys agree that this is not the kind of chapter you should leave out of a general chemistry course. I think it's really important.
The nuclear, is it refining? Those refining tubes, uranium enrichment.
Yes.
That creates. I checked on Google just a few minutes ago to see what they look like, and it generates nuclear fuel. Is that correct?
Right. So uranium itself, uranium ore would not be good for fuel at all. You have to separate out the uranium-235 from all the other isotopes. And that's what it's doing.
It's refining it.
Yeah, it's separating out uranium-235. It's just purifying uranium-235.
So when you have uranium, when you have pure uranium-235, is it, I mean, is it a liquid form?
No, it's a solid.
It's a solid?
Mm-hmm.
And then you would put that into the reactor once it's completely refined. And then the reactor would generate the heat and the steam.
Exactly, right. Mm-hmm.
Okay.
Yeah, tremendous amounts of heat. It's just unfathomable. So that's the reason
why
it's effective.
When a nuclear reactor has an overload, we could take a more recent example in Japan. I'm a little unclear as to, how it overloads and what happens, why people have so much suspicion about it, why it's so dangerous.
Well, here's a brief scenario about what happened in Chernobyl, the worst disaster ever. So first of all, it's kind of like the government in Hawaii. I asked my son, hey, how'd you get that job? Oh, my friend. So it's kind of that way. The Communist Party is very much into nepotism and everything else.
Yes.
So that's how you get these important government jobs. It's not how good you are, how smart you are. It's like who you know, who's your family, that kind of BS.
Right. Right.
And so there was scheduled to be a test of the power system. And they already been told by the people working at the plant that no, we shouldn't do this because we need to put more water in here. We need to get the cooling system top notch before we do this stress test on it. And somebody said, no, we have to get it done because it's scheduled and I don't want to look bad. So they went ahead and did it anyway. And that's what caused that disaster. It was a human problem. It was not a technological problem.
And in that case, is it the ore that, or the refined ore that overheats and causes a meltdown, or?
That's exactly right. Yeah, they put too much fuel in there. If you and I were running a nuclear power plant, we would not put so much fuel into the reactor that something like that could happen. We'd put a little bit in at a time, a little bit more when we needed it. And we certainly wouldn't take a chance of, driving around the island with not enough oil in our car. But that's what they did.
I see.
In the case of Fukushima, it was a natural disaster, which the original people who planned and designed the power stations were aware of and took advantage of. But then when it came to actually building it, parts became so expensive that they did some shortcuts. So for example, the reason that happened at Fukushima is because the secondary cooling systems were also destroyed by the tsunami. Because to save money, they put the secondary cooling machines down the hill where it should have been up the hill, way above where the power plant actually was, to be farther away from the ocean. But that would have cost a lot more money. And so they saved money instead of going with the original plan. That's the kind of problems that happen.
Okay. Okay.
Yeah.
Thank you. Interesting.
Yeah. Okay, so chapter 7 is not going to be on the exam. Chapter 8 is where we need to go next. So I'm going to share the screen. Chapter 8. And so I want you to understand things. I mean, a lot of this stuff is pretty difficult to understand, but I'm not going to say, oh, it's hard to understand, so just know this. Okay, I'm not that kind of person. There's a whole lot of things that you can get, even if you don't understand the whole thing exactly. And after a while, when you see the big picture, things start to fall in place if you just keep at it. So, again, periodic law and the creation of the periodic table was based upon practical observations, not necessarily on theory. So elements were placed into groups based upon their properties, right? So now you have this periodic law. We need to have theories now to understand why does it work this way. So in the early 1900s, Einstein came up with special relativity, general relativity. Right after that, Niels Bohr showed that the arrangement on the periodic table correlated to electrons on the surface of the atoms, as we call valence electrons. And then Heisenberg, with his uncertainty hypothesis, stated that, you know what, we cannot know both the energy and location of electron. And just think how simple this is. So people are spending all their time trying to figure out, well, where is the electron? And Heisenberg was in that same boat. So finally he figured this out. We will never really know where an electron is. If we invent a machine, let's say it's what's a good word for it? Say we have a probe, and we're going to take that probe and put it up next to the electron to measure where the electron is. What is that probe going to be made out of? Atoms. And on the surface of atoms are electron clouds. So I bring this electron cloud next to an atom I'm trying to measure, an electron I'm going to try and measure. And what happens? You move the electron that you're trying to measure. So the process of trying to find out where the electron is going to move the electron. So basically it was important because it said, well, forget about trying to find where the electron is. We'll talk about what is the probability of the electron being here versus the probability of the electron being somewhere else. So at that same time, de Broglie had showed that all particles can behave like waves, including electrons. Then Schrödinger came along and said, you know what? I'm going to turn all of this information into some kind of a mathematical model. And the mathematical model was not based upon regular math. It was based upon statistics. It was all probability. So he kind of invented a new form of mathematics to take advantage of the probability. What is the probability that the electron is going to be found here versus found over here? So when they finally finished a couple of the equations, most of them could not be solved. People wouldn't live long enough. Computers at the time couldn't do that. Even when I was a grad student, you know, they had calculated the mathematical solutions to the Schrödinger equations for only a few of the elements. So anyway, here's a couple of things about light. Here's what ocean waves do. Ocean waves diffract. And you might be, well, you've seen this, but you don't understand why. Matter of fact, I think a lot of physicists don't know why. It refracts because of the the attractive forces between water molecules. That's the reason why they do that. But nevertheless, we see this diffraction. So here's a very important experiment that was done during this time in the early 1900s. So here's the source of light. So here's the light coming through this large opening. You see no diffraction. But when you make it into a smaller diffraction, you see diffraction. So what if the wave, what if the electron did not act like a wave and do diffraction? What if it acted like a particle? Well, then it's very obvious that the particle would come and it would like get past here and keep going, but when it got here, then you wouldn't see anything. So you would not see this diffraction at all. Same thing over here. A particle would go right through here, hit this and then stop. Then a few of them would go right through here and keep going in a straight line. There wouldn't be any diffraction. So the reason why we see diffraction with light is because light behaves like a wave. So here's another type of diffraction. You take light, like white light, and you shine it at this diffraction gradient, which is a rough gradient, but the roughness is repeatable. And so here you see all kinds of different scattering patterns. And when it scatters, you see that it gets diffracted into the rainbow. Here's another way of looking at it. So you get these orders of diffraction, and you're basically separating them out just like you would in a prism. So from this, we understand that electrons and light have both particle properties and wave properties. So here's a website. If you really wanted to know more about the type of mathematics, you can go here. But here's an example for the helium atom. So when you start to solve this, you have all this mathematics that are really quite high level. So what I'm going to do now is show you that the solutions to the Schrodinger equations are the shapes of the orbitals. Okay, so what are we looking at here? An s orbital. This is shown as a probability map, and this is simply the balloon model. Now, as far as I'm concerned, the balloon models have not advanced anything at all. They just make it more complex, make it harder for students to understand. And I often ask myself, well, I've had discussions with other chemists, I'm like, how'd they come up with this balloon model stuff? They just like hired a clown from somebody's birthday party or something? Anyway, it just misleads students as far as I'm concerned. So if we look at this, the probability of finding the electron out here is nil. The probability of finding the electron here is a little bit greater, then over here it's greater, then even here it's greater. Even this is misleading, because where does it look like the electron is most likely to be found? Right in the center of the sphere. And what is in the center of that sphere is the nucleus. So my question to you is, do you expect to find the electron in the nucleus? The answer is no, it's not allowed to be there. So therefore, this is misleading, and so is this. Now, when we get to a p-type of orbital, then here's the nucleus right here. So you see that there's no probability of finding the electron in the nucleus. As you go out this way, here's a lobe where you have a high probability about here, and another lobe with a high probability out here. So what they do in the balloon model is do this, essentially. So right at that intersection between X and Y and Z is the nucleus. But as you'll see later, in a p subshell, there's actually 3 orbitals. So here's the one on the Y, here's the one on the Z, here's the one on, well, that's the Z, here's the X, okay? And what happens when you put all of these together? You get something like this. So here's an S, smallest S, here's the next S, and then comes a P. And so when you put all the P's together, it does look spherical, doesn't it? But individually, they are not spherical. So how does the electron move around? The answer is we don't know. And where did these models come from? The Schrodinger equations. These are the solutions to the Schrodinger equations. And they were looking at the probability of finding the electron here versus out here. I finally found a book in a very, very unlikely place that showed you the D and F orbitals. And notice something. The S's are very simple. There's only one lobe. And then the next more complex one, there's two lobes. Then the next most complex one, there's four lobes. But look at all the different combinations. And then look at this one. What the heck is that supposed to be? Is that some artist who was also a policeman and really liked donuts? No, that is the mathematical solution to the Schrodinger equation. So then if you look at the highest level, it gets even more lobes, more complex. So here's another way to look at it. Here's the most simple, and N is the shell. Notice that the shell gets higher, there's more electrons in it, and it gets more complicated. So this is the simplest. And then you get to shell number 2, you also have that one, but you have P's. You get to shell number 3, you have that one P's, then you have D's, because you got more electrons. And you get to shell number 4, you got even the F's now. And then this is a problem for me because they just leave out these other ones over here. I mean, I'll show you why they do that, but essentially if n equals 5, it's even more complex. It should go way out past this, but they don't do it that way. So here's what I want you to see. Here's an S type of subshell. Here's where the electron moves around. We find the electron here. Right there is the nucleus. Okay. So what I've done is I've taken a cross section. So let me see. Okay, I can see myself. So you have a spherical object, right? What I drew there is I took a slice out of the middle. So you're looking at a slice that I took through here. And you see that there's the nucleus. There's no electron probability around there. As you go out to a certain point, you have a high probability of finding electrons. If you go past that, there's zero probability of finding the electrons. Same thing for a P. Okay. So anyway, so in an S type of subshell, there's only one orbital, right? So it is just what it is. For a P type of subshell, you have 3 of them. So you have 3 of these going together. In a D shape, you have 4 lobes, but there's 5 of them all going together. You see it gets more and more spherical. So here I tried to give you the kind of explanation that I think should be in textbooks. So I took that slice out of the sphere. Here's the nucleus. And notice that now the high probability is dark, but the probability is like, well, maybe I'm going to find a little bit there, and maybe it's going to be a little bit there, but out here it's not going to be there. So now if I take a density meter and I ran it through here, look, I got 0 probability, and then, oh, I got some probability here. Now I have a high probability, and then it goes down to this, and then it goes like this again. And right in the middle is going to be where the nucleus is. For a P type of subshell, it's similar. So I got a low probability here, then a high probability, and then it becomes low again, right? And then 0. So you see where the nucleus is. So the electrons have a high probability of being here and here. Then with a D, where it's more complex, yeah, you have a high probability wherever you see the dark spot. What? Sorry. Where'd my other one go? Okay. So I'm sure you understood every single word of that, or you think that I'm totally crazy, but I think it will start to make sense as we go through this. So when we talk about where an electron is in an atom, we're not really talking about a physical place. What we're talking about is the energy that that electron has. So here's the scenario. If I had the electron in the nucleus, we would call that zero energy. Because remember, the protons in the nucleus are positively charged. The electron outside the nucleus is negatively charged. So to have them apart is a form of potential energy. If I let them go together, the potential energy is like minimum. So the premise is, the further I take away that electron, the more energy it actually has. So no electrons are allowed to be in here, but electrons are allowed to be here. This is shell number 1 right here. Okay.
Excuse me, Professor, I had a question.
Mm-hmm.
If the electron is closer to the proton, doesn't it become a neutron?
It will combine and become a neutron, that's right.
Okay.
And we saw that in electron capture.
And that's why it has a zero energy, right? Because it's closer to that of a neutron.
Right, exactly.
Okay. Okay, I see.
So that means that you can't have electrons here, but out here you can. So here there's more energy than here. So the further away I take the electron, the more energy it is. And you know why that makes sense? Think about electricity. In electricity traveling through the wires in your house, are those electrons actually associated with a single atom? Or do those electrons have so much energy that they move around as current, almost independent from the atom where they derive from? So that helps us with understanding that concept. And here's another concept. Say we're talking about an electron that was found here in the 2s. If it's normally found there, that is the ground state for that electron. That's the lowest possible energy for that particular electron. It can't go that way because these electrons will repel it. And it can't go that way because it takes energy to go farther away. So that's the ground state for that particular electron. Now, what if that electron somehow were to gain energy, gain kinetic energy? What would happen to it? It would get so much energy, it's vibrating so quickly over here that it has to jump out into a higher energy orbit. Now, that's called the excited state. Does that make sense? So electrons can either be where they're naturally found, that's going to be the ground state, or if they gain energy, they're going to jump out into what's called the excited state.
Does the electron have to be in the valence shell to be considered in the excited state?
No, because those electrons that are associated with electrical current, those are valence electrons, and they're not even in the orbits anymore.
Okay.
Yeah. So Niels Bohr developed the idea of quantized energy levels for electrons in about 1913. And we used the Bohr model of the atom to explain what we're doing right here, even though we know it's wrong. So what is wrong with this? Well, we know by looking at the solution to the Schrödinger equations, in other words, the shapes of the orbitals, that the orbitals are not spherical like this. So right now, it's very difficult to even explain things without having the simplicity of saying, oh, what if they all are in circular orbits? Then we can talk about the energy between this one and this one, right? So look, in this 1s, we have 2 electrons, and now it's full. Look at how the symbolism is used. 1s2, what does that mean? These electrons, of which there's 2 of them, are in shell number 1. They're in a type of subshell that's an S, and there's 2 of them. What about in this second shell over here, in shell number 2? In shell number 2, you have 2 subshells. One's an S and one's a P. I have 2 that are in the S, and I have only 1 that's in the P. So you see how that works? So I don't know, I just thought these guys were funny. I mean, so here's Heisenberg, I think. Here's Schrödinger, probably. Here's Bohr. This is what got me onto this, because Bohr looks like he's in a boy band or something, you know? Here's de Broglie, the wave guy, but he never surfed. Here's Einstein. He looks pretty old there. So valence electrons are the surface electrons. Those are the reactive electrons. Those are the ones that are found in the highest numbered shell. And the number of valence electrons is given to you by the group number on the periodic table. So if they're not valence electrons, they're going to be core electrons. So core electrons are the inner electrons, those that are not on the surface, and those are the ones that are not reactive. So if you're a sodium electron, and sodium decides to lose an electron and give it to chlorine to form chloride, for example, what kind of electron is that? That's a valence electron. So how many valence and core electrons in sodium? It's element number 11, so it's got 11 protons, therefore 11 electrons. So it's in group 1, that tells me that it's got 1 valence electron. So therefore the other 10 are going to be core electrons. So what about bromine? Element number 35, so 35 total electrons, is in group 7. So 7 valence electrons and 28 core electrons. So what about helium? So helium has 2 electrons and it's in group 8. What? Because helium is the runt of the family. It's in that family because the properties of that family, the noble gases, is that they're inert. So we're going to go over this again on Monday. We have only a few minutes, but I want to give you the big picture so we can dissect the big picture a little bit more detail on Monday. So electrons are found in shells, subshells, and orbitals. So what is a shell? It's simply a general volume where you find an electron. If you look at the periodic table, we don't need more than 7 shells. So here's shell number 1, 2, 3, 4, 5, 6, 7. We don't have any more atoms. That's all we need. But the shell number can be used to give us some information. For example, how many electrons can you get in that shell? It's given by 2n squared. And n is the maximum number of subshells. So in shell number 1, you have 1 subshell. Shell number 2, you have 2 subshells. It's very simple. What is a subshell? A subshell is a more specific volume where you find electrons. And we only need 4 different subshells to cover all the elements on the periodic table. Okay, well, what is an orbital? An orbital, also known as a wave function. Why? Because we know electrons behave like waves. And a function, because we use Schrödinger equations to figure out what they look like. That's the most specific volume where you find in electrons. And an orbital can be completely empty. It can have either 1 electron or it can have 2 electrons, and that's it, and it's full. Okay. So the figures that we saw earlier are pictures of the orbitals or wave functions. They were the solutions to the Schrödinger equations. Okay, so I'm just trying to get you the big picture so that when we come back on Monday, we can get into a little bit more detail. Okay. So for example, I'm going to show you this. Here's the S's, here's the P's, here's the D's, and here's the F's. Okay. So all this correlates to the periodic table. So does anybody have any questions before we take off for the weekend?
For Chem 100, the test will be available Monday and Tuesday,
Yes. Yeah.
and it expires at midnight on Tuesday. Yes.
No, it goes 9 to 9.
So 9 p.m. on Tuesday.
Yeah. Uh-huh.
Okay.
So you should be done by 9 p.m. on either Monday or Tuesday.
Okay.
Yeah.
And I can just go on the portal, and the instructions will be listed under tests and quizzes. Yes.
Yep. Mm-hmm.
Okay. Thank you.
Yep. And I sent out that that file, what to expect on exam 1, and I put some information on there. Yeah.
Yes. Yes, I have that.
Okay. Well, you guys have a great weekend. If you got questions, just email. And okay. So take care.
Thank you, Professor.
Thank you.
Take care.
Thank you.
Bye-bye.
Have a good one.